Hi, my name is Albert Wood. I am a postdoctoral researcher at the National Taiwan University, and I recently finished my PhD at UCL under the supervision of Felix Schulze. I study geometric flows, in particular Lagrangian mean curvature flow. So mean curvature flow is a natural and well-studied parabolic flow of submanifolds in Riemannian manifolds. Explicitly, it's the flow such that each point in the submanifold moves in the direction of its mean curvature vector. And it's the gradient descent for the volume function on submanifolds. So one might hope that mean curvature flow results in long-time existence and convergence to a minimal submanifold. Unfortunately, this is not always the case, and sometimes singularities of the flow form. An interesting application of mean curvature flow is in the study of Lagrangian submanifolds of Kähler manifolds. Knut Smoczyk proved that in the case where the ambient Kähler manifold is Ricci flat, the class of Lagrangian submanifolds is actually preserved under the flow. In other words, if you start with a Lagrangian submanifold, then as the flow progresses, the submanifold remains Lagrangian. This is somewhat surprising given that mean curvature flow is a concept in Riemannian geometry and Lagrangian submanifolds are a concept of symplectic geometry. So again, a natural question to ask is whether Lagrangian mean curvature flow exists for a long time and converges to a minimal Lagrangian representative in the homology class, also known as a special Lagrangian. Indeed, there is an ambitious conjecture to this effect by R.P. Thomas, S.T. Yao, and D. Joyce. However, as in the general case, singularities may form along the flow, and so an understanding of when these singularities form and what they look like is vital for progress with this conjecture. In my talk, I hope to expand further on the nature of these conjectures and give the state-of-the-art knowledge on singularities of mean curvature flow and singularities of Lagrangian mean curvature flow, explaining how the two cases are different. Rather surprisingly, singularities of Lagrangian mean curvature flow turn out to be very different in nature to singularities of generic mean curvature flow. Thank you very much to the organizers for inviting me to give a talk at this online conference, and hope to see you all soon.
Hi, I'm Weibo Su. I'm currently a postdoc at Academia Sinica in Taipei. My research interest is in calibrated geometry and geometric flows. I'm mainly working on problems related to the existence and uniqueness of special Lagrangian submanifolds and Lagrangian mean curvature flow. Roughly speaking, special Lagrangian submanifolds are volume minimizing submanifolds, and Lagrangian mean curvature flow is the negative gradient flow of the volume. And so people want to use Lagrangian mean curvature flow to find special Lagrangians. However, finite time singularities often occur and cause obstructions to the long-time existence of the flow. And therefore, it is necessary to study the geometry of singularities. In my talk, I will be focusing on the special kind of solutions to Lagrangian mean curvature flow called the Lagrangian translating solitons. Under the Lagrangian mean curvature flow, these submanifolds evolve by translations in the Euclidean space. And these kind of submanifolds are important because they provide possible local models for the finite time singularities. And therefore, through studying them, we may gain information or properties of the singularities for the flow. I will first compare the theory of Lagrangian translating solitons with special Lagrangian geometry. And we will find some similarities between these two kinds of submanifolds. Then I will be describing a gluing construction of new examples of Lagrangian translating solitons, which is essentially an analog of the gluing construction of special Lagrangian submanifolds. Using this construction, we are able to construct families of interesting new examples of Lagrangian translating solitons with more complicated topology than the known examples so far.
Hi, my name is Lucas Ambrozio. I am an assistant professor at INPA, the Institute of Mathematics Pure and Applied, in Rio de Janeiro, Brazil. I wish I could show you the view of my office window, and also show you a glimpse of the Southern Hemisphere summer. But due to the coronavirus pandemic and a busy term at IMPA, I am recording this from home at night. I have become interested recently in systolic and diastolic invariants of Riemannian manifolds that are somehow related to minimal submanifolds, and this will be the subject of my talks. Systole and diastole are moments of the periodic movement of the heart. Systole is the moment of contraction, and diastole is the moment of expansion. In the first introductory talk, I will try to give you some intuition of why I say that certain geometric invariants of Riemannian manifolds have a systolic or a diastolic character. This will be done by concrete examples. One of them is related to talks by other speakers in this conference. In the second talk, I will discuss systems of Riemannian projective planes of dimension 2 and 3. In the third lecture, I will discuss diastoles of Riemannian spheres of dimension 2 and 3. The focus will be always on comparing these invariants to the ambient volume. I plan to speak about some well-known results, about a couple of open problems, and about a bit of my own work on the subject. To finish this video, I would like to congratulate Hojo Lee for conceiving this online event and thank him for the absolutely fantastic organization. In these times, when some of us are perhaps reflecting about the meaning of things, I do feel this format of event, where we speakers have been asked to conceive presentations, having in mind mostly the young people beginning their journey in geometric analysis, is most welcome. I wish you all a very pleasant time while watching the videos of this event, and I look forward to interact with you in our remote Q&A session. Take care, and I see you.
Hi, I'm Artur Saturnino. I'm a PhD student at the University of Pennsylvania, and my main interest is in variational problems related to minimal and CMC surfaces. My presentation will be divided in two parts. The first part will be expository, where I will introduce the Morse index, give an intuition as to what it means, and present some classical results that relate the Morse index to other geometric and topological quantities. In the second part, I will talk about the degeneration of sequences of CMC surfaces with bounded index, and I will use such sequences to show some results that relate the index to the area and to the genus of CMC surfaces embedded in general tree manifolds and in spherical tree manifolds. Lastly, I would like to thank Hojo Lee for putting together the seminar and for giving me an opportunity to present some of my work.
Hi everyone, my name is Jingze Zhu. I'm currently a PhD student in Columbia University. My research interest is the geometric flow, particularly the mean curvature flow and their singularities. In this event, I'm going to focus on the mean convex mean curvature flow singularities. I will begin with some background and introduction to the previous results, and then I want to talk about my recent result. It says that a special class of the singularity models in R4, which is the convex non-collapsed translating soliton, must be SO2 symmetric. I will outline the proof. Lastly, I want to thank Professor Hojo Lee for organizing this wonderful event.
Hi everyone, my name is Yangyang Li. I'm a graduate student at Princeton University, working with Fernando Coda Marcus. My recent works are related to minimal surfaces and unbrain-piece min-max theory. Minimal surfaces are important geometric objects in differential geometry, which also occur naturally in our real life. They also have a lot of applications in other fields, such as positive mass theorem in general relativity, positive scalar curvature, and so on. The ungrain-pit min-max theory is a fruitful theory to search for minimal hypersurfaces in a Riemannian manifold. And the recent development has led to a lot of breakthroughs in differential geometry, like resolving Wilmot conjecture, Yau's conjecture, and others. However, minimal hypersurfaces in high dimensions could behave differently from those in low dimensions due to the existence of singularities. We know that when the dimension of the ambient manifold is no greater than 7, then every minimal hypersurface should be smooth, but this is not true in higher dimensions. Although these singularities, the singular set are relatively small, they will invalidate some generalization of techniques from low dimensions to higher dimensions. And it has been long conjectured that one should be able to resolve these singularities generically. In the talk, I will speak about my work with Zhihang Wang, who is also a graduate student at Princeton. I will show that in dimension 8, one can perturb away singularities to obtain a smooth minimal hypersurface. In other words, we obtain the general regularity of minimal hypersurfaces in dimension 8. Thank you.
Hello, everyone. My name is Draryn Chang. I'm a postdoctoral fellow at the University of Waterloo, which is in Ontario, Canada. And I hope you're all doing well during this time. I'd like to thank Hoju for the invitation to speak at this workshop. It's always good to have an audience, and it gives me the chance to reflect on what I've done on this topic that I'm going to speak about, which is the relationship between Ginzburg-Landau functionals and minimal submanifolds. So the objective of my talks is to describe one particular aspect of this relationship, namely whether it extends to the stability and Morse indices of the critical points of the functionals. So Ginzburg-Landau on the one hand and the volume functional on the other. So the talks will be given in 3 parts. In part 1, I will give a general overview of just how the Ginzburg-Landau functional relates to minimal submanifolds. And in part 2, I will recall some classical theorems on the classification of stable or low index minimal submanifolds. And then I will state some previous and recent results that can be viewed as Ginzburg-Landau analogs of these classical theorems on minimal submanifolds, both in terms of the statement and in terms of the method of proof. Finally, in part 3, I will indicate how some of these Ginzburg-Landau analogs can be proven. So that's roughly the plan. And if you're really interested in this direction, then I recommend that you also check out the talks by Daniel Stern at this workshop. In any case, I hope this would be a fulfilling experience for all of you, and I look forward to meeting all of you online. So thank you in advance for your attention, and thanks again, Hoju, for organizing this and for inviting me.
Hi, I'm Daniel Stern. I'm a postdoc at the University of Chicago working in geometric analysis. My research touches on a few different topics within geometric analysis, like minimal submanifolds, harmonic maps, other geometric PDEs, as well as scalar curvature and spectral geometry. It's great to see many of these topics represented in the events of this workshop, thanks in no small part to the hard work of our organizer, Hoju, to whom we're all very grateful. In these lectures, I'm going to talk about the geometric and analytic features of 2 of my favorite families of PDEs, the complex Ginzburg-Landau equations, which arise in the study of harmonic maps and superconductivity, and the self-dual abelian-Yang-Mills Higgs equations, which have played a prominent role in low-dimensional gauge theory over the last 4 decades. Both of these families exhibit intriguing, but qualitatively very different relationships with minimal submanifolds of codimension 2. And these relationships will be the primary focus of this mini-course. In the first of 3 lectures, I'll give some important background information from the study of minimal submanifolds in geometric measure theory, and review some key results concerning the relationship between the scalar Allen-Kahn equations and minimal hypersurfaces, which will motivate our search for analogous phenomena in higher codimension. In the second lecture, I'll introduce the complex Ginzburg-Landau equations and describe some of the major developments in their analysis over the last 30 years. In particular, I'll explain the subtle relationship between solutions of the Ginzburg-Landau equations and minimal submanifolds of codimension 2, describe some recent advances in the existence theory of solutions on general manifolds, and discuss some deep open problems concerning the blow-up analysis of solutions. In the third lecture, I'll introduce the self-dual abelian Yang-Mills Higgs equations. After reviewing important early results of Taubes and Hong, Yost, and Struve concerning the behavior of solutions over two-dimensional domains, I'll describe some recent work characterizing the behavior of solutions in general dimension. These results reveal a correspondence between solutions of these equations and minimal submanifolds of codimension 2, which is strikingly similar to the classic correspondence between the Allen-Kahn equations and minimal hypersurfaces, and provides us with a valuable new tool for producing minimal submanifolds of higher codimension. All right, I hope you enjoy, and I look forward to seeing you in the question and answer sessions.